Hello student, in this video we will learn about topic 8 thermodynamics. For this video we will only be learning the first two subtopics, which is 8.1 temperature and the zeroth law of thermodynamics, and 8.2 thermometers and the temperature scale. The first one, temperature and the zeroth law of thermodynamics. Before we begin, we firstly need to understand the thermodynamics terms. The first one will be heat. Heat is defined as the process by which energy is exchanged between objects because of temperature differences. The energy mentioned here is actually thermal energy that is actually transferred from one object to the other due to difference in their temperature. Moving on, objects that are in thermal contact if energy can be exchanged between them. Moving on to the third one, thermal equilibrium exists when two objects are in thermal contact with each other and there is no net exchange of energy between them. Now, we will be using all of thermodynamics terms that we have learned just now to understand the zeroth law of thermodynamics. We learned the zeroth law of thermodynamics to give new definition to the temperature. Before this, you may have learned the temperature as a quantity that shows the degree of coldness or hotness of an object. Before we take a look at the new definition, we're firstly going to define the zeroth law of thermodynamics. We can refer to this diagram for further understanding. If object A and B are separately in thermal equilibrium with a third object C, then A and B are in thermal equilibrium with each other. When two objects are in thermal equilibrium, there will be no further heat transfer occur. Because of this, we can say that the temperature is the property that determines whether or not an object is in thermal equilibrium with other objects. Two objects in thermal equilibrium with each other are at the same temperature. Let's learn 8.2 thermometers and the temperature scales. Thermometer is used to measure the temperature of an object or a system. Thermometers make use of physical properties that change with temperature. Many physical properties can be used, for example, volume of a liquid, length of a solid, pressure of a gas held at constant volume, volume of a gas held at constant pressure, electric resistance of a conductor, or color of a very hot object. A mercury thermometer is an example of a common thermometer that uses volume of a liquid as its physical properties. The mercury inside of the thermometer increases in its volume due to thermal expansion. Moving on, this is also another example of a thermometer, and in this case, it is a Galileo thermometer. It is a thermometer made of a sealed glass cylinder containing a clear liquid and several glass vessels of varying density. So we have several glass vessels here which represent different temperature. The individual glass vessels will rise or fall in proportion to their respective density and the density of the surrounding liquid as the temperature change. Thermometers can be calibrated by placing them in thermal contact with an environment that remains at constant temperature. The environment could be a mixture of ice and water in thermal equilibrium. Also commonly used is water and steam in thermal equilibrium. Referring to this diagram, we have uncalibrated mercury thermometer, which is placed initially in this ice-water mixture. The ice-water mixture will have this temperature of 0 degrees Celsius. So we can put a scale on the cylindrical part of our thermometer. Moving on, we can put the thermometer inside of this water steam mixture, and then we know that the temperature should be 100 degrees Celsius, and we put a scale on the cylindrical part of the thermometer. The distance between these 2 points is divided into 100 segments or 100 degrees. We have seen how the Celsius temperature scale is related to the freezing point and boiling point of water. Now we will take a look at absolute temperature scale. For this purpose, we will be using the constant volume gas thermometer. Temperature readings are nearly independent of the gas as long as the gas pressure is low, and the temperature needs to be well above the temperature at which the gas liquefy, meaning that we can repeat the experiment with different gas as long as the gas pressure is low as well as the temperature is above at which the gas liquefy. Pressure varies with temperature when maintaining a constant volume. We can imagine a gas here inside of this flask is heated. So when the temperature rises, the volume is also going to expand. We have thermal expansion of the gas. What happened here is actually to make sure that it is exactly at the zero scale, we need to increase the pressure. In order to increase the pressure, we can move this reservoir B upward or downward in order to modify the pressure, as long as the mercury and gas boundary here is actually at zero scale. With that, we can plot pressure temperature graph, and then as mentioned here, all gases extrapolate to the same temperature at zero pressure. This temperature is absolute zero. So if we repeat 3 trials using different types of gas, we can plot this graph. This solid line for trial 1, it is this brown line, and we have the blue line, the solid blue line for trial 2, and then the green solid line for trial 3. We can extend this line until it reaches this intersect, and then this point is actually pointing to the absolute zero value. So the absolute zero value is equal to 0 Kelvin, or equal to negative 273.15 degrees Celsius. In this case, we have this conversion from one temperature scale to the other, which is the Celsius temperature scale to the Kelvin temperature scale. So far, we have learned 2 temperature scales that are Celsius temperature scale and absolute temperature scale. For the Celsius temperature scale, the unit is in degree Celsius, and for the absolute temperature scale, the unit is in Kelvin. The third and the last one is the Fahrenheit temperature scale. It is the most common temperature scale used in the United States. Temperature of the ice point is 32 degrees Fahrenheit, and temperature of the steam point is 212 degrees Fahrenheit. There are 180 divisions between the points, which are the ice point as well as the steam point for the Fahrenheit scale. The Celsius and the Kelvin scale will have a total of 100 divisions between these 2 points. If we have the 3 thermometers for each of these temperature scale and place them side by side, we can see that the ice point 0 degrees Celsius is equal to 32 degrees Fahrenheit. It is also equal to 273.15 Kelvin. As for the steam point, 100 degrees Celsius is equal to 212 degrees Fahrenheit, equal to 373.15 Kelvin. In order to convert among these 3 temperature scale, we need to use these 3 formula. For the first one, Tc is equal to Tk minus 273.15. This equation is used to convert from Kelvin to Celsius. Moving on to the second equation, Tf is equal to 9 over 5 Tc plus with 32. The second equation is used to convert from Celsius to Fahrenheit scale. And last but not least, delta Tc is equal to delta Tk equal to 5 over 9 delta Tf. This is actually for the temperature difference or the change in the temperature, since the Celsius and the Kelvin scale will have 100 division between the 2 points, which is the steam and the ice point. They are having the same scale of 100, meaning that the change in the temperature will be the same. However, for degrees Fahrenheit, as you can see here, we have a much smaller scale because they are in total 180 divisions. You have to multiply with 5 over 9, multiply with the change in the temperature, change in Fahrenheit scale. And another thing to note is actually you cannot directly convert Kelvin into Fahrenheit. If you were to convert from Kelvin to Fahrenheit, firstly you need to convert from Celsius, and then from Celsius scale, you can now convert to Fahrenheit. Let's take a look at an example. Convert 318.15 Kelvin into Fahrenheit scale of temperature. To do that, we firstly need to convert this Kelvin into degrees Celsius.